In this video, you and I get to implement a site-to-site VPN tunnel using a virtual tunnel interface. Let's begin. One of the classic ways of doing a site-to-site IPsec VPN tunnel was to use a method that involved crypto maps. And the crypto maps would be applied to the interfaces that the peers would be using to communicate with each other. And inside the crypto map, it was a big if-then statement. If traffic matches the crypto ACL, then set the IPsec transform, specifying a transform set that we'd created, and also set the peer. So in the life of R1, if traffic is trying to be sent out this interface where the crypto map is, if that outbound traffic matches the crypto ACL, then the router says, oh, I need to set my peer to be 35003, which we'd have defined in our crypto map. And with that peer, set up IPsec using the transform set that I've configured. Now, all of this is IKE Phase 2. Now, to set up IKE Phase 2, we need to have an IKE Phase 1 tunnel in place. So the next thing that R1 would do is say, do I have an IKE Phase 1 tunnel between myself, R1, and R3? And if the answer is yes, it would use that IKE Phase 1 tunnel to build the IPsec tunnel. Again, this is with traditional IKE version 1 with the 2 phases. And if R1 did not have an IKE Phase 1 tunnel with R3, R1 would then go ahead and start an IKE Phase 1 negotiation with R3. So they do the whole haggle, the Diffie-Hellman, the authentication, and then with that IKE Phase 1 tunnel in place, they would kick over and negotiate the IKE Phase 2 and set up the IPsec SAs. Now, one of the challenges with this is that not all traffic leaving this interface on R1 is going to be encrypted. So let me put the IPsec tunnel in green, which represents our 2 IPsec security associations, one going this way and one going this way. So some of our traffic, for example, traffic from 10.1.1 going to 10.3.3, that will be going over the tunnel. But if the user Bob is going out to, for example, CNN.com, that traffic will not be going through the tunnel. It's just going out the outside interface, naked or clear text over to CNN. Now, one of the challenges with that is, what if we wanted to have certain types of manipulation or features applied to IPsec traffic, but not to the clear text traffic, or vice versa? Using crypto maps, there wasn't a really clean way to apply, for example, policy A to clear text traffic and policy B to the encrypted traffic. And when I'm talking about policy, I'm talking about policies such as network address translation, quality of service, access control lists, etc. So to help separate that and make it a lot easier to both implement IPsec and to put different policies on different types of traffic, we can use the IPsec virtual tunnel interface feature on the iOS router. Now, to do this, we're going to create a tunnel interface on both routers, router 1 and router 3 in this example. So let's use tunnel interface number 1. And if we are using static virtual tunnel interfaces, we're going to identify the source and the destination for both sides. So we'll say tunnel source on R1 is 15.0.0.1, and from R1's perspective, the tunnel destination is 35.0.0.3. Now on this tunnel interface, we can give it an IP address. So for this tunnel, it's very likely we'd choose one of the RFC 1918 address spaces, such as the 10 network, or the 172.16, or the 192.168. And for the 10 network, that'd be a /8 or longer. And on the /16, it'd be a /12 or longer. And on the 192.168, it'd be a /16 or longer regarding the masks for that RFC 1918 address space. However, another option is that we don't have to assign this tunnel interface on each router. We don't have to give it its own IP address or IP subnet. We can use a feature called IP unnumbered. And we could tell the tunnel interface, hey, we're going to use unnumbered. We're simply going to borrow an IP address that's already existing on the router. So if R1 has a loopback of 1.1.1.1 and R3 has a loopback of 3.3.3.3, we could just tell the tunnel interface, hey, we want to do IP unnumbered, and we're going to go ahead and borrow the IP address that's currently on the loopback 0 interface. Or some other interface that has an IP address. It's simply going to make the tunnel interface be a copycat. And it's logically going to use that same IP address. And this is one of those weird situations where we can have this tunnel interface be 1111 copying loopback 1, and this tunnel interface over on R3 being a copycat and using 3333, and yet routing protocols like EIGRP and OSPF, they'll be happy to become neighbors over that unnumbered interface. Even though the two sides with IP unnumbered are not on the same subnet, like 1111 and 3333, IP unnumbered simply says to those routing protocols, it's okay, just go ahead. Now, one of the cool features of using this virtual tunnel interface is that if we want to apply certain types of policies to the encrypted traffic, we can apply that policy directly to this tunnel interface, this virtual tunnel interface. So if we wanted to do a QoS policy and do marking of the packet in a certain way for the IPsec traffic, we'd create that policy, very likely with a class map and a policy map, and we'd apply that policy map to the tunnel interface. And then all the traffic that's going out that tunnel interface would get that policy. However, if we wanted a different quality of service policy, or maybe a different NAT policy on the physical interface for clear text traffic that's going out the router, we could apply that policy to the physical interface. So there's a very clear separation regarding the policies for clear text traffic, which is applied to the physical interface, compared to policies that are going to be applied to the IPsec traffic, which would be implemented on the tunnel interface. Now, in our previous videos together in this course, we used to have R1 and R3 as part of a dynamic multi-point VPN topology. But for now, what we're going to do is we're going to create a site-to-site static VPN tunnel using virtual tunnel interfaces. So I just want to make sure that we're clear that the old tunnel 0 interfaces that we were using for DMVPN, I want to make sure that those are shut down and not in use because I don't want them to interfere with our site-to-site configuration for virtual tunnel interfaces. So we'll tear those down and we'll create new ones. We'll create tunnel 1, and that'll help give you a nice and visual difference as well to make sure we remember which tunnels we're working with for the static VTI. And we'll also create a new transform set and a new IPsec security profile that will apply to both of these tunnel interfaces. So first things first, let's go into interface tunnel 0 on R1, and I'm going to simply use the command shutdown just to make sure there's no trace of DMVPN configuration that's active on this router. Let's create a brand new transform set using the syntax crypto IPsec transform-set, the name of our set, which we'll call P2P-set, and we'll use AES-256 and SHA-HMAC. We'll also make sure that we're going to use mode tunnel. Now, because we're doing a site-to-site VPN, for the benefit of users like Bob, to get to a server that's over here, we want tunnel mode because we want to take the original source address from Bob and the original destination address and tuck those or hide those inside of the ESP payload and encrypt the whole thing. And by default, a transform set, even if we didn't manually specify tunnel, will use tunnel mode by default. Let's also create an IPsec profile that will apply to our new tunnel interface that we're going to create here in a moment. Crypto IPsec profile. We'll call this P2P-profile, and we'll simply set inside of that profile the transform set that we just created. As we follow the bouncing ball here, this IPsec profile, when we apply it to a tunnel interface, it's going to go ahead and call on the transform set called P2P set, which is using these IPsec transforms. And just to get a clear picture of what's on this box before we continue any further configuration, let's do a show run pipe section crypto and take a look at all of our crypto related commands. So here's our IKE phase 1 policy that we created earlier in DMVPNs. We can still use that. It's perfectly fine as long as we have a compatible IKE phase 1 policy on both peers. Because we specified pre-shared key, here is our pre-shared key that we can use with anybody because we're using the wildcard. We have our old transform set that we use with DMVPN. Here's the new transform set that we just created. You'll notice it's not showing us in the config that it's mode tunnel because that's the default. Here's our old IPsec profile that we used in DMVPN that called upon the transform set called our set. Here's the IPsec profile that we just created that's going to call on the transform set P2P set. On R1, I do have a loopback of 1.1.1.1 with a 32-bit mask, and on R3, I have a loopback of 3.3.3.3 with a mask of 32 bits. So for the new tunnel interface that we're going to create, let's create interface tunnel number 1, and let's go ahead and use IP unnumbered, and we'll point to loopback 0. So effectively, this new tunnel interface here on R1 is going to borrow the IP address of 1.1.1.1. Now in a static point-to-point tunnel, we're going to specify both ends of the tunnel, the source and the destination. So in R1, the source IP address for the tunnel is going to be 15.0.0.1, and the destination of this tunnel is going to be 35.0.0.3. So for the tunnel source, we could either put in the IP address of 15.0.0.1, or we could simply point to the interface serial 1/0, and it'll use the IP address on that serial 1/0 interface. Either way is fine. For the tunnel destination, we're going to specify that it's 35.0.0.3. And now that we have both the source and the destination defined, the interface has come up. Hey, hooray! So earlier it was down when we just brought it up. That's because we hadn't defined the source and destination. And now it's claiming to be up, but that's going to be short-lived once we use this next command, which is tunnel mode IPsec IP version 4, we could be carrying lots of different types of traffic. We're going to be operating on this tunnel as an IPsec version 4 tunnel. And as a result, because we don't have a current security association set up on that tunnel with the other side, we've just gone to a down state. Now that'll be corrected once we get R3 up and running. Our last step is to apply the IPsec profile to this tunnel interface. And the syntax for that is tunnel protection IPsec, the keyword profile, and the name of our IPsec profile. And we have a little happy message saying Isaac Hemp is on, meaning, hey, I'm willing to go ahead and receive IKE Phase 1 negotiations from a peer, as well as I'm willing to create and initiate IKE Phase 1 negotiations if I need to. Now the challenge is that even if we do set up tunnel 1 here and tunnel 1 over here on the other side, and the actual number of the tunnel interface isn't critical, it's the ingredients that go into that tunnel that are the important part. But even if we set up both sides, how in the world is R3 going to know about the 10.11 network? And how is R1 going to know about the 10.3.3 network? We need to have some information regarding routing. So we can either do static routes. We could tell R1, hey, to get to 10.3.3, go ahead and route it out your tunnel interface. And vice versa for R3, we could say, hey, to get to the 10.1.1 subnet, go ahead and route that out of your tunnel 1 interface. And because these tunnels are a point-to-point link, we could certainly point to the egress interface and make that work. Or, check this out, we could add a routing protocol on top of it. So we already have EIGRP, Autonomous System 777, running on R1 and R3 from our previous configuration with DMVPN. And in that EIGRP configuration, the 10 network is already included. So what we could do is we could say on R1, please include the 1.1.1.1, which is our loopback, and it's also being used by the Tunnel 1 interface because we're using IP unnumbered right there. So if we enable the 1.1.1 address as part of EIGRP, and we do the same thing over here on R3, we enable the 3.3.3.3 as part of EIGRP for Autonomous System 777, then over this tunnel interface, router 1 and R3 can become EIGRP neighbors. So we'll simply go into router configuration mode for Autonomous System 777, and we'll add network 1111. Now we could just say network 1000 and catch everything in one, but if we want to be very granular, I'm using the wildcard masks of 0000 to say only the IP address that matches exactly those 32 bits. Let's go over to R3 and we'll finish the configuration over here. So let's create a transform set right here on R3. We'll use the compatible transforms that we had over on R1. And I'm going to specify mode tunnel as well for this. We don't have to because it's a default, but I wanted to impress upon your minds that the default behavior of a transform set is going to be used tunnel mode. And if we're using DMVPN, we want to specifically specify transport mode. But here in Site2Site VPNs with VTIs, tunnel mode is perfect. Next, let's create our IPsec profile here that's going to call on that transform set that we just created. We'll call this profile P2P-profile. And the name of the actual profile isn't the critical part, it's the ingredients that go into it. Let's do a quick verification check too, just to make sure we see exactly what the cryptography components are right here on R3. So we'll do that with a show run pipe section crypto. And here's our IKE Phase 1 policy. We know that's compatible from our DMVPN exercises. It matches exactly what R1 has. We have a compatible IKE Phase 1 key. Here's the transform set that we just created. And here's the IPsec profile that calls on that transform set that we also just created. That looks great. So here in R3, we'll create tunnel interface number 1. We're going to use the IP unnumbered trick here as well. We'll specify the source is our local serial 1/0 interface, and the destination is the reachable outside address of R1 at 15.0.0.1. So initially said it was down, and then once we have a source and destination specified, it's gone to up. And now that we use the command tunnel mode IPsec IPv4, because we don't have a current security association in place, it's going to go back to down until we get that SA. Now to assist in that process, we need to apply the IPsec profile to this tunnel interface. And the syntax for that is tunnel protection IPsec profile and the name of our IPsec profile, which in our case was P2P-profile. And that is great news. So the interface has changed to up. The next thing I want to do in R3 is add that loopback address space inside of EIGRP Autonomous System 777. And it's really not the loopback we're after. However, the tunnel interface is using that address. And as a result, if we include that 3333 inside of EIGRP, the tunnel interface will now become a part of EIGRP And we should be able to form an EIGRP neighborship over with R1. So we'll go into router configuration mode for Autonomous System 777, and we'll add the 32-bit IP address of 3.3.3.3 as a network statement. And EIGRP, being as quick as it is, brought up the adjacency right away. Now here's my question. How would we go about verifying that we have an IKE Phase 1 tunnel? I know we obviously do because we got an adjacency over that connection. However, if we wanted to see that we had an IKE Phase 1 tunnel currently in place, what command would we issue? And if you're saying, hey Keith, I know, that's show crypto isocemp SA, you'd be absolutely correct. So here's our current IKE Phase 1 security association. And if we hit the up arrow key and type in the word detail, it'll give us the nitty-gritty regarding that IKE Phase 1 tunnel, including the remaining lifetime. Another command that we could use is show crypto engine connection active, and that will show us a bird's eye view of our IPsec security associations and our IKE Phase 1 security associations. So here's our IKE Phase 1, and here's the two security associations we have for IKE Phase 2. They're two unidirectional tunnels, one going from us to R1, one from R1 to us. And most of the traffic that we're seeing is very likely due to the EIGRP hello traffic that's going back and forth consistently between R1 and R3. If we wanted to verify our EIGRP neighbors, we could do a show IP EIGRP neighbors, and we should have just one, Mr. R1, at the address of 1.1.1.1. To verify the routes that we've learned via EIGRP, we can do a show IP route EIGRP. So R3 has learned about the 10.1.1 subnet, that's right here. And it's also learned about the 1.1.1.1 32-bit address, which is currently being shared by the loopback interface on R1 as well as the tunnel interface on R1. And if we want to verify full connectivity between both subnets, we can do a ping over to the 10.1.1 subnet, source it from our local 10.3.3, and there we have full connectivity. And if we want to take a look at our interface IP addresses just for fun for that unnumbered feature, we'll do a show IP interface brief. I'm going to ask it to exclude in the output any lines that have the word unassigned in it, because R3 has additional interfaces that are going to clutter up the screen. So right here we have our tunnel 1 interface with 3.3.3.3, which is borrowing, if you will, the IP address from loopback 0 due to IP unnumbered. And tunnel 0 interface was the IP address that we had used for DMVPN, which we shut down earlier in this video. And what I think would be really fun for you and I to do right now is let's do a quick demonstration of how we can apply a certain policy to traffic that's going over the tunnel interface, which is our encrypted traffic, and a different policy for traffic that's going in clear text. And at the end of the day, it's going to boil down to this. Whatever policy we apply to the tunnel interface is going to apply to our encrypted traffic. Whatever policy we apply to the physical interface will apply to clear text traffic as it's being sent out the router. In a Cisco environment, the concept of a class map and a policy map and a service policy command set is very common. We have it on the ASA, they call it Modular Policy Framework. We have it on the iOS, and the idea is with a class map identifies traffic. The policy map says how it's going to manipulate the traffic. And the policy map is going to call upon the class map for the identification. And then the service policy is how we actually apply it and where we apply it. For example, do you want to apply that policy map to the serial interface? Or do you want to apply a policy map to the VTI, the tunnel interface? So in our example, let's create two class maps. We'll create two policy maps. And then with the service policy, we'll apply one of our policy maps to the VTI, the tunnel interface. And the other policy will apply to the physical interface. So we can visually see different policies, one for encrypted traffic and one for clear text traffic. So here in R3, I'm going to create two class maps. The first one I'm going to call VTI-class. It's going to say, please match on anything. And for our second class map, let's call it serial class, and let's have it match on anything. Now the benefit of having two separate class maps is that we can put those into two different policy maps and be very clear what we're referring to. Also, if we want to see the existing class maps on this system, we can do a show class-map, and we have three class maps. We have the two that we just created that match on anything, and we have the default class map called class-default. So effectively, any of these three class maps, if we call on them in a policy map, they're going to match on all traffic that's seen. Next, let's create two policy maps. The first one we'll call VTI-map. It's going to look for traffic matching the class map called VTI class, and if we see that traffic, we want to manipulate it and set the IP precedence to a value of 2, just as an example. Now, for the benefit of comparing and contrasting, let's create a second policy map. We'll call this one serial-map. We'll say we want to look for traffic matching the class map called serial-class. And if we see that traffic, the manipulation is going to be we're going to set the IP precedence to a value of 4. So now we have two different policies. One that says I'm going to set IP precedence to 2, and another one that says I'm going to set IP precedence to 4. Now I've got a question for you. Which of these policy maps do you think we are going to apply to the physical interface on R3 versus the tunnel interface on R3? And if you're saying, Keith, well, based on how you named it, it's very likely we're going to apply the serial policy map to the physical serial interface for clear text. And that'll change for clear text traffic the IP precedence to 4 in those IP packets. And the VTI map we're going to apply to the tunnel interface, which will make the IP precedence in the IPsec protected packets be changed to an IP precedence of 2. So there's a clean example of two different policies, one being applied for clear text traffic to the interface and the other being applied to the tunnel interface for the encrypted traffic. So if we want to see all the policy maps we have configured on the box, we'll do a show policy-map. And here's our two policy maps. Now we need to apply those policy maps appropriately. Let's do the interface tunnel 1 first. We'll go into interface tunnel 1 and use the command service-policy output VTI-map. Now, any traffic that goes out tunnel 1 is going to have the policy map called VTI map applied to it. And VTI map says, okay, any traffic that matches VTI class, which is anything, we're going to go ahead and change the IP precedence in the IP header to a value of 2. Next, let's go ahead into interface configuration mode for serial 1/0 and use that service-policy command output and apply the serial-map policy for interface serial 1/0. And now, respectively, any traffic that is going out the serial interface, this is unencrypted traffic. Because the policy map called serial map is applied to it, it'll look for any traffic based on the class map called serial class, and it will manipulate the IP header and set the IP precedence to a value of 4. One of the things that I love to do is verify that when we implement a command or a feature that it's actually working. Now, how in the world do we verify this? Well, one way would be to do a show command of show policy-map interface tunnel 1, and it should show us hit counters regarding the traffic that it's seen and the actual manipulation regarding that policy map that's been done to that traffic. So on this interface of tunnel 1, we have the policy map of VTI map. That's matching on the class of VTI class. It's seen 27 packets so far, and it's manipulated or marked 27 packets with the IP precedence of 2. Now I thought it'd be fun to bring up a packet capture and take a look at the traffic going back and forth. This is a live capture off of the serial 1/0 interface of R3. And so if I stop that capture, and we take a look at one of these packets that's going from 35003 over to 15001, and we look at the IP header information, the DSCP class selector of 2 equates to an IP precedence of 2, which are all related to the TOS bits in the IP header. And I've just saved this file in the Nugget Lab files for this course. It's called IPsec with IP precedence set to 2. So if you want to take a look at that and review that, you're welcome to do that. Now, what about the physical interface traffic? Let's take a look. Let's do a show policy-map interface serial 1/0 and take a look at how much traffic is going through that interface and how much is being marked. So on this interface, we have the serial map applied. We have 43 packets that have gone through that interface. However, it's showing us that we have packets marked equals 0. And that's because we are not sending any clear text traffic, or haven't yet, on this interface. Now we can fix that. If we want to send some clear text traffic, we can just do a ping of the outside interface of R1 at 15001, and that would be sent as clear text out the interface. And just for grins, let's go ahead and do a ping. Let's do a repeat count of 3. And that'll be very identifiable in the output. We'll use the up arrow key a couple times, do a show policy map for interface serial 1/0, and check this out. Packets marked 3. So the policy map applied to the physical interface is going to apply to non-encrypted traffic. And if we wanted to capture that, I've just started the capture in the background. Let's go ahead and do that ping again of 3 pings. We'll go back to our capture. I'll go ahead and stop the capture. And if we go to the outbound traffic here from 35003 going to 15001, if we open up the IP header and look at the DSCP information, you'll notice we now have a class selector of 4. And that's because in our policy map we said set IP precedence to 4, which equates to this value in the DSCP bits. I've also saved this capture file as well in the Nugget Lab files, and I've named it naked IP with IP precedence set to 4, if you want to take a look at that as well. I have had a great time with you in this course, and my recommendation would be to practice. Practice everything we've done together in this video in your own lab environment. And to assist with that, I've also included this document called VTI point-to-point static, which includes all of the syntax that we use together in this demonstration that you can use as a resource as you lab this up and practice with it on your own. And this file is in the Nugget Lab files associated with this course. So again, thanks so much for joining me. I had a great time. I hope this has been informative for you, and I'd like to thank you for viewing.